One.
Good morning to those tuning in to today's webcast presentation of oilfield tracers, the facts, the myths, and the legends. It's my pleasure to introduce today's presenter, Patrick Hayes, the North America Business Development Manager at TracerCo. With over 15 years at TracerCo, Patrick has established his expertise in chemical tracer technology by managing projects across the globe, improving efficiencies and capital investments for upstream, midstream, and downstream business units. For those unfamiliar with TracerCo, it is a world-leading industrial technology company that has developed and used tracer diagnostics and measurement tools in a number of different industries. Behind the scenes, it has improved safety, security, and technical understanding through activities as varied as fuel security programs, cutting-edge radiation monitors, and of course, oilfield operations. Its reservoir group has over 40 years of experience helping oil companies understand the movement of fluids within the reservoir and help them make informed decisions that affect their drilling, completion, and production strategies. In today's talk, Patrick will cover the history and background of oilfield tracers, provide a discipline-agnostic understanding of how different tracer types are applied and interpreted, and explain how the knowledge and understanding gained from a tracer study can affect the financial bottom line. Afterwards, he and TracerCo's Global Marketing Manager, Paul Hewitt, will answer live any questions you might have about the presentation or tracer technology in general. With that, Patrick, let's begin.
Thanks for the introduction, Sidipja. As promised, today's presentation will cover a range of applications with some in-depth dives into the facts and myths revolving around tracer technology, including how to correctly identify types of tracers that might be required to meet your application needs and ensure a return on investment. We'll be starting with an overview of technology, where and why to use them, followed by a brief description of different applications. Once the presentation is completed, we will have some time for question and answers. I would like to encourage those with questions to use the Q&A tab on the upper right side of your screen. As Sidipja mentioned, Paul Hewitt will be looking at these during the presentation. Please sit back and relax and enjoy the presentation. We start with a look to the past to help us get to the present day by uncovering why some of the reasons for myths and legends are existing in today's oil field. It is also important that we define what can be a tracer, their limitations, and whether these meet our expectation in today's world. There are a lot of different tracers available in the industry. A tracer is only a dynamic measurement tool. This may sound very simple in concept. However, to gain the right kind of information, you need very specific tools at hand. The environment that the tracers encounter needs not affect their signature or behavior. If there are interactions with the reservoir environment, there will be an impact on the results. Stability is key to a success. Tracers for most diagnostics, where quantification of production and communication is the goal, must be foreign to the reservoir environment. In the early days of tracing, dyes were commonly used in the industry to track fluid flow. Yet interactions downhole with reservoir rock caused losses limited their use. I'll talk about the importance of quantitative analysis and calculations further in the presentation, and we'll elaborate a little more on this topic, as an example. Up until recently, radioactive tracers were popular for a variety of investigational purposes. The use of radioactive materials for near wellbore diagnostics, such as frac height and communication, are limited to a few feet of depth of signal. The gamma rays are absorbed by dense materials such as steel and cement, reservoir rocks, and fluids. This causes the data interpretation to be limited to close to the wellbore. When looking at the needs for horizontal diagnostic applications, we are also limited to a few unique identifiable radioactive isotopes. They are limited by half-life decay And of course, health and safety management during use and disposal can be risky. With the advancements in tools and detectors, many naturally occurring tracers can be present to provide value as well. Naturally occurring markers are also present and can be used to identify rock properties, facies changes, and compartmentalization of zones of production. Such examples are logs, DNA, and stable isotope mass spectrometry. Relating these to the quantity of production can be difficult or impossible, not phase specific and not tied to production. The advancements in research and development, both in the laboratory and in the field, has changed how we quantify tracers and qualify their results. Chemical tracer technology has evolved to measure things previously thought to be impossible. But using the right tracers for the right applications is critical to getting flow knowledge to maximize your return on investment. The misuse and misunderstanding of tracer properties has provided a lot of room for failed projects, incomplete data, rumors, myths, and misunderstandings. So what makes a tracer successful and another not? We often hear concerns, and some of those concerns are very valid. The stability of tracers in reservoir, as well as after being produced, is critical. Several things can affect stability, such as the chemistry of the injected fluid. Exposure to high temperature can be problematic for many compounds thought to be good tracers. Exposure to high temperatures can significantly impact project outcomes. The tracers need to be designed to be phase specific in most cases. If you're told that only the gas or oil can be traced at one time, it should be a warning sign that tracer is partitioning. And the understanding of its behavior must be looked at much more closely. The tracers must not be naturally present, easily detected for the project duration, present little to no hazard to the environment or people, and commercially viable, of course. We've covered a few myths and legends from the past, and now we need to get to the present day tracers and applications. I've grabbed a few examples of tracers and where we have progressed over time, starting from left to right. The old radioactive tracers were limited in their availability of only a few uniques. They were hazardous and required logging in many cases. Many times, inferences had to be made to relate to production. If it produced water, the industry presumed that this location was where the oil and gas was coming from. The phase-specific chemical tracers now shed light on individual phase production of oil, water, and gas. The lower limits of quantification, non-hazardous nature, and quantitative capabilities have changed the oil and gas industry and how it measures production, gains efficiency, and speeds technology development. With large numbers of unique tracers available, further granularity can be provided. The next generation of tracers, combined with new analytical capabilities, has brought forth the ability to measure remaining oil in place and residual oil measurements in both inner well and single well tests, further enhancing data during EOR chemical pilot studies and enhancing capabilities of design improvements to reducing CapEx and OpEx risks. I mentioned some of the important tracer properties earlier regarding the limits of quantification, LOQ, and tracer detection. I've heard many stories told to me by engineers about historical projects with tracers that appeared and disappeared, like magic into the wind. The ability to capture useful data is often linked to the analytical capabilities of what's being measured. At the top right, we have a chemical tracer signal in blue versus a dye in purple. The filtration of the downhole environment has flattened the curve of the signal and diminished its true value, whereas the full curve can be seen in blue and more in-depth information can be made and used in models if needed. When calculating the distribution of injection, the breakthrough, peak, mean, and mode are needed to make many of the calculations. The bottom right presents the difference between two different pieces of equipment with different LOQs, limits of quantification, analyzing the same sample. Some instruments may have different background signals, limiting the limits of quantification and lowering the concentration, cause lower quality data. We've walked the path of tracers through time and their detection. Now we must look at how tracers can be applied. The best tracers can be ruined if applied incorrectly. Each application has its benefits and its faults. There are solid ways of tracing and liquid applications. Though none of the four below are the same in what they can do and the analysis that can be performed on the data. We start on the right with the particulates that are qualitative. Second from the left are the controlled release tracers and are encapsulated and designed for linear release to provide longevity. Liquids are quantifiable, and then there are partitioning tracers on the far right based on a passive partitioning two-tracer component measurement. We'll have to take a closer look to remove the facts and the fiction from all of these. I mentioned solids, but there is a difference between types of solids, as they are not alike in what they can measure. Particulate tracers on the left have many issues that cannot be resolved, making them only qualitative and limited to yes or no phase flow answers. The line graph next to the particulates shows the erratic release rate of 18 unique tracers absorbed into porous media and then as a group placed into a single stage of a well. I'll go into a bit more detail on this topic a little later in the presentation. The right is controlled release tracers that are encapsulated and placed on a downhole completion tool as a polymer. The known location, tracer designed release rate, and phase-specific chemical nature can provide much insight when understood. We can take a little more time to elaborate, as this is a common question I get asked. I mentioned qualitative results from solid tracers. As this is true, if the exact location of a tracer is known, we can confirm production from that location during steady state operations as yes or no. When water or oil tracers are placed side by side in a known location, we can go on to the next step and provide relative water cut data, as the amount of tracer flow to the surface from each position within a well will be directly proportional to the surface area contacted by each position within a well will be directly proportional to the surface area contacted by the water versus the oil. More water will result in a larger tracer response from the specific portion versus the other. However, we cannot get volumes being produced of the liquids during steady state analysis. We must look to another analysis approach to quantify zonal contribution. This utilizes a pulse velocity measurement and decay curve analysis, looking at the time to surface of the tracer pulse formed in the well and the shape of the curves as they decay back to steady state conditions. This then makes for a tracer production log, or what we refer to as a TPL. More details on this type of analysis in part 2 of this presentation series in October. The real difference between solid and liquids is in the data and what can be made of it. Liquid tracers provide a direct quantitative measurement of phases being produced. Solid particulates can provide a limited analysis for a qualitative yes or no result. The porous media and depth of penetration of tracer during the tracer loading into the material changes the amount of tracer per volume present. The placement volume, contact surface area with the intended phase flow, the flow rate across the material. With a high flow rate, you get a low concentration per volume. And low flow rate, you get a high concentration per volume. Temperature effects and solubility in different oils all affect particulate tracer release rates. Whereas the deployment method of a liquid tracer and its hydrophilic chemical nature makes for tracing of the hydrocarbon fracture matrix. This allows for better understanding of the network that is producing and quantification of the flow. Liquid molecular water tracers are passive tracers and do not interact with the rock properties or partition into the oil. The passive properties allows for numerous observations to be made, from quantifying well-to-well communication, characterizing the communication, and quantifying production. Liquid oil tracers are immiscible in the water while being pumped, but have a strong affinity for the oil phase, their K factor. And due to the hydrophilic nature, they get out of the water when contacted by movable or immovable hydrocarbons. It is important that the K factor is very high, and this alone can be a major difference between tracer data and the providers. Understanding the tracer behavior requires extensive testing, research, and development. One myth is to calibrate to the field properties. It is not possible, and formation changes from area to area can be drastic. You must have extensive research to ensure the reliability of the tracers being used, extensive knowledge of the characteristics, and conduct testing at reservoir conditions across cores, under pressure, and temperatures over time. We will start to look at a few data sets and break down the information, starting with some raw data. The evaluation looking at concentration alone, presented in the top blue bar graph, does not take volume into account. This provides for a false trend in production and can greatly skew the interpretation, especially when we start to look at multi-well pads and different volumes being evaluated for different wells. When evaluating the mass recovery and taking volumes into account, we can establish relative stage phase production trends and quantify the production from zones, stages, interwell communication, child and parent relationships. Often, even with taking into account normalized percentages and barrels produced, is required to interpret the production or communication over time. It is the mass recovery of tracer that delivers the return on investment when evaluating both enhanced recovery projects and stimulation projects. Not using mass has set many of the historical foundations for many myths, misunderstandings, and confusion surrounding tracer results. For EOR projects, the flow patterns can be analyzed by looking at the breakthrough, peaks, mode, and mean. Projects can be made more efficient using extrapolation calculations, shortening the project timelines, and reducing analytical costs. Further to this, valuable quantitative measurements can be made to determine swept pore volume, calculate complexity of flow, and reservoir capacity, and more. When evaluating horizontal wells to determine the best landing targets, geology, completion, and artificial lift data sets are used in combination to evaluate the phase production over time. Starting at the top right, the right-hand y-axis presents the total produced for the time frame the sample was collected, the little black dotted line. The left-hand y-axis presents the production in barrels for each of the trace stages. This helps us understand contribution and what stages affected the phase recovery over time and how changes influenced downhole production behavior. The middle graph presents the cumulative tracer recovery on the right-hand y-axis in percent, and the cumulative production on the left-hand y-axis. This helps us visualize performance, but also tracks the remaining tracer in the reservoir. If a stage has produced most of its tracer applied and no longer is detected, it's likely the amount of remaining tracer is too low to be detected. However, the opposite can be said for a stage with the majority of tracer remaining that is no longer present. This is very important supporting information when evaluating if a stage is no longer producing or the tracer is possibly depleted. The bottom graph is the one I find most useful. The cumulative average relative production present in the large blue bar provides an overview and areas of interest. And for each of the stages, trends over time from left to right allows us to look at both the stage's overall performance and how it performs in the longer term. This is particularly important as different completions, geology, and zones may produce differently early on than later in time. In this presentation, we can see that the toe stages to the right has diminished quickly, while stage 2 through 7 have become dominant performers as time progressed and continued to increase. There are many common applications and projects for chemical tracers, and these are often categorized into sets such as inner well, inflow, and near wellbore as the main groupings. But the applications are dependent on the goals and needs. In today's world, many of the applications have become intermingled and multi-purposed. The lines drawn between both unconventional technologies and conventional completions are blurred, with both benefiting from the advancements of one another. Now many more uses are available that may be less well known, such as huff and puff evaluations, remediation effectiveness, and target evaluations. In many cases, several project objectives can be accomplished as part of a single project design, most of the time with little or no additional cost. However, it is very important not to put primary goals and objectives in jeopardy for the lesser important ones that may complicate the results. The tracer application will be dependent on the goals and objectives of the project. Many times they are added during constant hydraulic fracturing operations. Some objectives require a lot of detailed attention during application of tracer phase to be able to quantify the intended results. DIY tracers or do-it-yourself tracers can be applied by the operator designee under simple procedures for flow verification. A big benefit to cost and reduction on on-site personnel. EOR projects usually require a pulsive tracer to be applied during steady injection. Inflow controlled release tracers often can be applied during lower completion manufacturing, saving on deployment mobilization costs and time on the drill site. Sampling strategies should always be challenged to ensure they secure the intended objectives. A common mistake is not sampling enough and analyzing too many samples. This sounds a lot like a bit of contradiction. However, we cannot analyze a sample we do not have, but let's be smart about what we analyze. Doing this brings efficiencies to both projects, both in investment and in return. If in doubt, collect samples. Before and after choke changes, for example, is in the event there is a discrepancy from expectations when placed on production. If not needed, simply don't analyze them. For EOR projects, analyze a sensible number of samples, skipping those that are not needed. This can create a huge savings. However, if early breakthrough is possible under a worst case scenario, it is better to collect more samples early on as not to miss important data points or miss a critical flow channel. Further refinement to the sample program can be made as data presents itself. Tracers are a rapid, cost-effective way to gain insight into complex reservoirs where interactions of multivariables make simulation and analytical description difficult. Chemical tracers have a proven track record of delivering a greater return on investment for operators by providing important reservoir flow insight. However, the success of a tracer study is dependent on using the correct tracer the right way. Know what you want from a study so you know what to look for in a tracer. Part 2 in October will cover design considerations, sample reporting, and data integration for projects to ensure a better return on investment. A detailed review from start to finish of case studies and how to use tracers for enhanced field productivity will be provided. In this webinar, we will address through case studies how chemical tracers help to provide significant insight during unconventional well design and completion. We will also discuss EOR enhancement opportunities and validate the effectiveness of an EOR strategy in conventional wells using interwell tracers with remaining oil saturation measurements, and by using long-term controlled release tracers for continuous profile of well production performance over an extended period of time. As a quick view of one segment of part 2, we have multivariables along with relative stage production over time. The solid bar shows the daily production and the translucent grid the cumulative production over time. This adds significant value when looking to understanding short and long-term production. The success of reservoir operations is dependent on completion and reservoir development strategies that correctly answer the challenges of well design, geology, target zone selection, and reservoir complexity. In each case, these challenges ultimately relate to the understanding of oil, water, and gas production along the wellbore and their movement within the reservoir. With this, I'll hand things back over to Sudipja for the Q&A portion of the webinar.
Thank you, Patrick. You certainly covered a wide array of topics there. If I were going to try and summarize, I would say that you've managed to cover major tracer delivery methods like liquid additives and polymer tracers, how this technology has evolved from early dye and radioactive technologies, the key rules of thumb for when to apply the different tracer types, and of course, how mass balance calculations form the backbone of analytical interpretation. If you are looking for more information on tracers in general, please note the link on this slide that Patrick has provided, so you can see more information about oil field tracers, or of course tune into part 2 of Patrick's presentation, where he goes into more detail on water, flood, and frac tracer studies to build upon the foundation he laid today. Now, I'll be moderating today's Q&A session. For our listeners, please submit your questions into the Q&A chat box on your screen. We'll work to answer the most common or frequent questions that have popped up amongst today's audience. But if your question isn't able to be addressed in the time we have remaining, don't fret. The team from Tracerco has committed to answering all the questions we miss by email over the next few days, so please don't be shy in asking. With that, we're going to start with two questions that are actually related, which are, what is the temperature limit for chemical tracers, and does reservoir temperature have an important role in how tracers are selected for a project?
Yeah, I'll take that one on, Sudipta, if that's okay. It's Paul Hewitt here, the market manager, and thank you everybody for attending this webinar today. Reservoir temperature is really quite important when it comes to the selection of particular chemical traces, and we're being asked, does that have an impact? And clearly it does. The second thing is, what is the temperature limit for chemical traces to be used? We've actually carried out quite extensive studies in all areas of our chemical tracer technology, using appropriate equipment to build the reservoir temperature to quite extreme levels. And we've tested all the way down from ambient all the way up to 190 Celsius. I don't quite know what that is in Fahrenheit, but that is a very hot condition. And we did that not just for a short period of time, but we actually carry out the tests over a 12-month period, just to make sure that there's no sudden fall off in stability of the traces over time. So basically, we've got traces that we can actually apply all the way through from low temperature all the way up to 19 Celsius in temperature if needed. I think that probably answers that question, Sudipta, if I can just hand it back to you.
Thank you. Question number 2, why are nanotracers not part of your tracer options? And that one I'm actually happy to answer. So nano and microparticle tracers have been a sort of burgeoning area of tracer technology over the last couple of years. They are relatively cutting edge. They're actually something that TracerCo has invested a significant amount of time and energy into, and you will actually see a number of patents related to fluorescing carbon dots and things like that that fall into the category of these ultra small tracers. Now, this particular technology has certain advantages. These exceptionally small physical tracers essentially have very good behavior in terms of absorption to reservoir rock. Generally speaking, they are not absorbed by your prop and pack or your reservoir rock or things like that. But they do have a number of limitations because the technology is so new. I would actually argue that cost is actually a major limitation compared to conventional chemical tracers. Nano tracers, microparticle tracers tend to be relatively expensive. There's also a lot of unknowns about their transport behavior. That's not particularly well categorized. So understanding how nanoparticle tracers move through interconnected fractures is still something that's still being investigated both in academia and in industry. There aren't very many nanotracers available. So if you are fracking, say, a 40-stage well, and you would like to have a unique tracer in each stage, that is something that just wouldn't be achievable with nanotracers, simply because there aren't enough unique tracers available to do that sort of thing. And finally, you tend to find that with a lot of the nanotracers that are currently being written about in industry papers and the like, is that they tend to have issues with thermal stability. With the exception of a very small minority, most of them tend to actually see some degradation with time. And for these reasons, it's an avenue of technology that TracerCo is invested in and has a lot of potential for the future, but currently just does not compete well in terms of practical applications against the well-established chemical tracers that have been part of today's presentation. All right. Okay. The next question, how many wells has TracerCo run chemical tracers where you've also validated using fiber optics or PLT at the same time? Can you show actual case studies?
Yeah, I've got some information on that, Sudipta. We've actually approached this in 2 stages. The first stage was to validate are analysis methodologies by using a dedicated flow loop at a research institute and undergoing some blind tests with a major operator. The results validated the methodology that we're using, and so we moved on and we started to look at situations where we could compare PLT with our data. So far, we've done this in several wells. We've mostly in the Middle East, so we've carried this out in 2 areas of the Middle East. One is actually published within an SPE paper, and if anybody is interested, we can provide the reference for that SPE paper. The second isn't published yet, but it is part of our technical presentations, and again, we can share that information with the individuals. From a fiber optic perspective, we actually tested our technology against fiber optics in the North Sea, and it came out favorably as well. So in answer to the question, we have done some validation. It's not a huge amount. There's not a great deal of opportunity, because what you tend to find is the traces are used in many wells where it could be somewhat difficult or very costly to actually run a PLT or fiber optics. But we have got some data that we can share with people.
Excellent, thank you. The next question we have is there an on-site tracer analysis method available to make changes to injection strategy, for example, gas injection EOR? So the most honest answer I can provide here is that it's something that's being worked on. The idea of having a system that would allow you to trace and analyze in line with your fluid production or injection is something that's being developed, but is not commercially available. What you tend to see really is the next best thing, which is where we use tracers in a conventional way, but have either a lab very close geographically to the well sites in question, which happens a lot, of course, in areas that have a high concentration of business, like the Permian and things like that, or in some cases, actually a mobile lab, which can be moved on site and used there to basically do your analysis. The next question I have here is, how do you address chemical tracers' high percolation into the DFN, discrete fracture network, and as a result, the high rate of frac hit detection? So here I'd actually challenge the idea that it has a artificially high rate of frac hit detection. So with tracer technology, it has been oftentimes used to sort of see if zippered wells or nearby wells have overlapping stimulated reservoir volumes, if you have communication between wells, and oftentimes will give you some idea if you had a frac hit early after a stimulation event. But the idea that it's artificially high, I would say, doesn't hold up, because when you start looking at sort of parallel diagnostic tools, things like pressure buildup tests and microseismic, which have been run very often alongside tracers, you tend to find that supporting evidence that the number of frac hits you're seeing are actually happening. But the nuance here is that that interconnectedness of your stimulated reservoir volume doesn't necessarily stay open over the life of the well. So you'll oftentimes see with tracers a high rate of frac hits, but if you've designed the tracer study to last 2 months, 3 months, you'll actually see that your communication starts to die off as your reservoir and your stimulated reservoir volumes start to settle down, and you start seeing some of those overlaps in the discrete fracture network start to close and sort of choke off communication between wells. So I guess the answer is we don't address it because we feel that it represents the reality of your reservoir and fluid flow. The next question. What detection sensitivities can be reached using chemical tracer technologies? ppm, ppb, so parts per million, parts per billion?
Yeah, I can answer that one, Sadiptia. So we typically nowadays use HPLC or GC gas chromatography to carry out our analysis. We separate the individual components within a sample, and then we analyze using primarily mass spectrometry. And mass spectrometry has come on leaps and bounds over the last few years, where not only can you divide a molecule into one or two pieces, but you can actually divide it further and so take away the baseline. So typically our limits of quantification, limits of detection are now in many cases in the parts per trillion levels. So that's 10 to the minus 12 levels in the likes of water and gas, as well as in some cases oil. Okay.
All right. Our next question is comparison of parts per billion of concentration between stages seemingly does not allow flow trends to be determined. Why? Patrick, you actually covered this in your mass balance explanation. Do you want to try and rephrase what you presented to explain that?
Yeah, sure, Sadipja, I can definitely do that. So strictly concentration is not going to provide a quantitative volumetric solution for you. And I'll use the example of a parent-child well and massively different flow rates. If you have a parent well that's producing, say, 3,000 barrels a day at a concentration of 50 parts per billion versus a parent well that is producing, say, 200 barrels of a fluid phase per day, yet at 100 parts per billion. If all you did was actually look at the concentrations, you would make the assumption that the parent well was actually producing twice the volume. However, when we look at this in mass, you can see that actually the child well would be producing roughly 3.5 or 4 times as much as that parent well in the actual mass or grams being produced. So we have to take into account the volumes being produced. And this also relates back to the frac hit scenario where you were mentioning earlier in answering Sadipja, where if the tracer shows up, physically this connection occurred, but measuring the volume, the quantity, and how that takes place over time really gives you the definition that you're looking for in understanding, was that connection maintained? Was it short-lived? And how did that relate either to the stimulation practice that was being used with diverters or non-diverters, or the volumes and rates being pumped, and then of course natural fractures and other properties that we may know of the reservoir. So understanding the mass communication and working in the common unit. If you're just simply working in concentration, unfortunately that's not the way to quantify production. So hopefully that gets you there, Sadipja, if there's something else you'd like to add.
Well, I mean, there's also the pure chemistry aspect of it, which is different chemical families tend to be easier or harder to actually detect. And so if you're just looking at straight concentration, to try and say that concentration correlates to flow, you can oftentimes have a pretty big margin of error just based on the fact that tracer A is a little easier to detect than tracer B. When you start correcting or normalizing to mass and that sensitivity, you tend to have a more accurate representation of what's going on downhole. It also oftentimes will affect the price tag of a job. If you want to really compare across the board in concentrations and you want to try and minimize that margin of error, then you have to start really applying the same mass to every stage. If you have a very sensitive tracer, that oftentimes is overkill, and so you're paying for tracer you don't need when you can switch it over to a normalized mass relationship, reduce the price of the job, and get that same understanding. We have a follow-up to the EOR question. It's pointing out that in an EOR unconventional type relationship, understanding when gas breakthrough happens is important, and the time to determine that is important, so adjustments in the field can be effectively managed. And honestly, you don't necessarily have to have inline measurements to achieve that. So tracers are very oftentimes used, and we have a very big run history of using tracers to determine water breakthrough in water floods and gas breakthrough in gas floods. And when you have a rough estimate for when breakthrough is going to happen, you can start a sampling program, kind of giving you a margin of error before and after that expected event time. And the turnaround time to analyze a sample is relatively short. When you're basically just trying to see the presence of something, it can be done very, very quickly. There's no need to really have an inline measurement system that gives you an answer in minutes if you can get the same answer within like 24 hours usually. The next question, what is the difference between pulse injection and continuous injection?
Yeah, I can take that one, Sudipti, if you want me to.
Sure.
We would typically use a pulse injection normally in interwell applications. So when we're looking to survey a water flood or an injection gas project, basically we pulse the tracer into the ground, and we're looking for the shape of the curve and the mass recovered from the individual production wells. That gives us a lot of flow information, as indicated by Patrick during the presentation. Continuous injection tends to be done when we're looking to understand what proportion of, say, formation water versus injected fluid is actually flowing back to us from within a well. So for instance, if we were to put 1 part per billion of a water tracer into the water continuously going downhole, and it was flowing out of a different well, or if we backflow into the same well, if it was producing at half a ppb, then we would know that 50% of that injected fluid was flowing out from that particular point. And that's really the only time that we'd use continuous injection. Continuous injection has its challenges in terms of logistics, setting things up and maintaining the injection over time. Hope that answers the question.
Yeah, so if you do a lot of streamline analysis, that's also another spot where pulse injection really shines. In both cases, you of course have a measured time of breakthrough or communication. But with pulse injection, since you know the amount of time that you were injecting your tracer into the reservoir, by comparing that to the time between the leading front of your pulse being detected and when the final amounts are detected, you get some idea of competing streamlines of fluid flow in your reservoir that you could extrapolate into a reservoir simulator if you needed to. Generally speaking, TracerCo doesn't do that sort of analysis, but the data is there for your reservoir team to sort of play with. How does the cost of tracers compare to other reservoir/well surveillance options? Favorably. So the cost of different diagnostic tools varies geographically. Things like fiber optics or certain coil deployed tools are significantly cheaper in Canada and North America than they would be in Indonesia or Malaysia. But generally speaking, you tend to find that tracers are one of the cheapest forms of well surveillance, mostly because we're taking advantage of systems that are already paid for and present. In the case of monitoring, say, a frac job, you're pumping alongside the frac fluid. In the case of looking at water floods or gas floods, you're taking advantage of injection wells that are already pumping in water or gas or other fluids. There usually isn't a need to have your well shut down in order to run it, like you would have to do with things like a production logging tool. There's no, or even in some cases with coil tubing deployed fiber optics. So I can't give you a straight dollars to dollars comparison because it's going to depend on where you are and what sort of discounts you get from your service companies. But usually I would argue that tracers are, if not the cheapest, one of the cheapest options for doing sort of that reservoir diagnostics or well surveillance.
Sudipta, if it's okay, I'd like to elaborate on that just a little bit, because we often get focused on cost, and rightly so, and under the current working environment, I think there's a couple of things that also need to be taken into consideration is the very different things that one measurement tool is providing versus another. The tracer side of things, chemical tracers provide insight into communication in a quantitative nature. It gives phase specific flow information of gas, oil, and water. And in many cases, as you mentioned, a PLT where maybe you have to shut in, there's risks involved. There's the turbulent environment, and there has to be a weight between risk of, will I get the information that I need? Is there a risk to the monitoring method from a deployment perspective? And is there a failure risk from unknown factors, say, or mechanical design? And though chemical tracers aren't the end all be all, because there's definitely advantages to different technologies. From a cost perspective, it's competitive or less, as you mentioned, but from a project success side of things, there's very little risk involved. Operationally, there's very little risk, and there's also very little risk of failure of gaining the goals and objectives that you want. And anytime you put an investment in any kind of science tool, we have to limit risks across the board, from design, application, through analysis. And I think that's a big part of where the tracer technology comes into play, is the very little risks that it poses all the way across the board, from start to finish.
And coming from a sort of production reservoir background, let me also state that I love it when we have multiple sources of information to reinforce or sort of fill in the gaps for each other. So whenever possible, we also love to see tracers getting run alongside microseismic or 4D seismic, run alongside pressure buildup tests and other forms of diagnostics. So always a plus if you can have a sort of a collaborative strategy.
Yeah, totally agree, Sudipta, 100%. Yep.
We are apparently running out of time. I've been instructed to take 2 more questions, and for those of you who haven't gotten an answer yet, again, we will respond to everyone individually by email within the next few days. The next question we have is, how often should samples be taken in order to have a good tracer concentration curve? And the answer is dependent on what you're trying to determine. Generally speaking, you want to have a higher frequency of samples when you're expecting the most meaningful changes. So if I were looking at a fracked well, for example, generally speaking, I'd want to see, a sample every couple of hours to every 12 hours, very early in the life of that well, in order to get some information about that flowback period and initial behavior. Once the well has been online for a while and we've sort of gone to steady state sort of flow, then it's less important for me to have a sample all that often. I can do it weekly, monthly, whatever. For longer term, like interwell projects and things like that, same sort of behavior. If we're talking about, say, gas floods, water floods, I'd want to take a lot of samples around the time that I'm expecting breakthrough to occur, but the rest of the time I can sort of be intermittent. If I'm expecting some sort of operational change to affect my fluid flow behavior in the reservoir, I would want to probably increase the number of samples that I'm taking. So if I have a choke change, if I am bringing online artificial lift, those are times where I might go from that intermittent weekly, monthly sample where it's really easy to extrapolate between points to a very frequent sampling procedure in order to capture what I am doing to my reservoir with my changes to production behavior. Right. With inflow measurements, with interwell, again, you're going to see sampling rates usually increase. Those tend to be very frequent. So the short answer is it depends on your project, what you're trying to discover, and how many times you're making some sort of meaningful change that might affect sort of the transient behavior in your reservoir.
Can I just build? I'm conscious of the time, so can I just build on that from an interwell application perspective?
Of course.
Because a number of mistakes have been made in the past where a customer relies too heavily on his numerical simulator to predict when the fluid should break through, etc. And hence they set forward a sampling strategy that essentially takes not many samples or none at all, up to the point, as you've said, where the most important point appears to be. But in our experience, we really encourage people to prepare for the unexpected and make sure to take samples, especially in interwell, such that we will find those channels that may be occurring within the rock, etc., and define those channels through the tracer curve. So just a little add-on to your comments.
Okay. The last question for today is, it seems that tracer concentrations in produced fluids from particles or polymers does not directly relate to flow. Can these tracers only provide a yes/no answer to where well flow is occurring from wells? So the answer is that it is sometimes. Generally speaking, when you're talking about those infused particles, you can never really have a understanding of the mass balance. So those tend to really only be good for that binary yes, no, flow is occurring sort of question, because of the fact that it is very easy to have inconsistent surface areas and sort of dilution of the tracer from those particles. It's very easy for those particles to be stuck in localized flow that kind of skews the overall reservoir behavior. There's just too many unknowns that make it difficult to accurately have a mass balance. You can get a rough idea. I'm not going to say that you can't get some gut feel for how flow is happening, but you can't really accurately quantify it with particles. With polymers, you can, but only under a limited sort of scenario. So with polymers, you now have a better understanding of elution rate, because those are very well tested with polymers, and you have very consistent behavior, temperatures, things like that would affect elution rate. But to really quantify flow and say it's coming from this portion of my well versus this portion of my well, what you really need to do is allow those polymers to build up sort of a localized cloud of your tracer. And then as you bring your well online, you can now get a measurement of the temporal, of the time it requires for that cloud to be produced and be brought up to your sampling point. And so in that transition from a static place to a transient flow condition, you can now get a snapshot that says, this is how my produced fluids are distributed along my wellbore. But as you go to steady state, as your well goes online for a while, you lose that distinct sort of spike of tracers. You now just have sort of constant flow, and you are now once again relegated to binary yes/no flows occurring from this zone. However, with polymers, if you need to go back and get another snapshot, you can halt production for a period of time, rebuild a tracer cloud, and once again go from static to transient flow to get another snapshot of that flow behavior. And that might not necessarily be clear as I explain it with just words, but if you have follow-up questions, just drop me your email address and I will pull up some illustrations and some charts that will probably make it a little bit clearer about how that time-based measurement strategy works with polymers and for assigning fluid behavior, and why it does not work when you start going to steady state production. All right, with that, we are out of time. Thank you again, everyone, for listening. Thank you, Patrick, for your presentation today, and thank you, Paul, for the answers you provided during a Q&A session. Please dial in for part 2, and for those of you who did not get your questions answered, please look for an email from us as we try and give you that detailed answer to these very interesting questions.